Today we're going to look at some applications for exponential and logarithmic functions that use base E or the natural log. A lot of applications in science, in business, in sociology that use the natural log of E or the natural exponential function, E being the base of the exponential function. One of the first things we want to look at is population growth. We'll look at both population growth and decay, but there's a basic formula for population growth, and that is the population at whatever time is, the population at time t, is equal to p sub 0, where p sub 0 is your initial population, e to the k, which is your rate that it's growing, times time. And it is growth if k is greater than 0. And we know from a previous work that we've done with the natural exponential function that if it is growing, it's going to look something like this. Now, this population growth could be talking about population growth of people, population growth of money, of some kind of items, viruses. That's big in the news right now. There's not a lot of data to go back on, but I'm sure that after this year with the coronavirus that we'll be able to have some data that's useful in predicting the growth for the virus. But right now we want to look at a population growth of people. And the first example we're going to look at is population growth of the country of Ghana. I'm not going to write out everything, but I'll just give us some basic information. In 2013, the population of Ghana, which is located on the west coast of Africa, was about 25.2 million. Okay, so in 2013, the population was about 25.2 million, and we have the exponential growth rate. In other words, K, our exponential growth rate, is approximately 2.19% per year. So if we're putting it as K, it's going to be, if it's 2.19%, it would be 0.219. 2.19% translates for K into 0.0219. And we want to first find the growth function, the exponential growth function. So if we're asked for a function, we always need to put things in function notation, and it's going to look like that function. So we know we're going to have P at t. Our population at time 0 is 25.2. E to the k, 0.0219 t. And that simply is the growth function for the population of Ghana. Not too hard to do. Notice we have our initial population here and our growth rate here. Okay, next I want to estimate the population in 2018. So I've got to figure out how far away is that from 2013. So 2018 minus 2013 is 5. So I'm looking for the population when time is 5, because we're talking about 5 years. Excuse me. So our equation that we're going to use is the population at 5 is equal to, this is our function, 25.2 e to the 0.0219 times 5, and that's just a calculator answer. We plug that into your calculator, and you should get that this is approximately 28.1. So we're approximately 28.1 million people. It's not just 28.1, it's 28.1 million. So you want to be sure that you include that. If you did not get that answer when you plugged it in your calculator, stop for just a second, pause the video, and go back and try plugging it in again to make sure that you're getting the correct answer. Okay, the next thing we want to do is to see how long will it take for the population to double. In other words, if our initial population, this is our function, initial population e to the kt, and that was 0.0219t, how long is it going to take for that to double? Now, the reason I did it this way instead of writing out the 25.2 and then 50.4 is just so that you can easily see that if I divide both sides by the population at time equals 0, they just cancel out. And we end up with, let me go back to the white, 2 equals, well, it didn't go, but that's okay, e to the 0.0219t. And we learned in one of the previous sections, now that's a whole lot easier than trying to multiply all that out and then divide. So anytime we're doubling, we're going to be looking at something that's similar to this. Now, in order to solve this, we take the natural log of both sides. So I'm going to take the natural log of 2. And when I take the natural log on the right side, it becomes 0.0219t times the natural log of e, which we know is 1. So in order to find the time that it's going to take for this to double, I'm going to divide the natural log of 2 by 0.0219, and that gives me the time that it will take for this to double. Okay, plugging this into our calculator, and just a reminder, don't forget, you have to be sure that you close this parenthesis before you divide. We get that time is approximately 31.7 years after our initial year, which in this case was 2013. And you'll have several questions that are similar to this, and so just give the number of years after the initial year. So this would be the length of time it would take for the population to double. Okay, and then finally, I want us to see when will the population be 40 million. Okay, I'm trying to keep some of this so I can keep what K is. I want to know, for part D, when will the population be 40 million people? Well, we have our function that was P of t equals, what was it, 25.2 e to the 0.0219t. So I want to know, when is this going to be equal to 40 million? So 40 equals 25.2 e to the 0.0219t. And then we simply solve the equation, divide both sides by 25.2. And we get, let's see, 40 divided by 25.2 is 1. Tell you what, let's just keep it at 25.2 so that we are not working with decimals that may throw us off. I'm just going to keep that because that's an exact answer versus an approximation. So in solving this, this went away. Remember, we can take the natural log of both sides, the natural log of 40 divided by 25.2. It wouldn't be wrong if you put a decimal approximation. It's about 1.587, but if you chop it off, your answer is not going to be quite as exact. So the natural log of 40 divided by 25.2, remember that equals to 0.0219 t times the natural log of e, which is 1. So t is the natural log of 40 divided by 25.2. This whole thing's in parentheses, divided by 0.0219. Let's put that in real quickly. The natural log of 40 divided by 25.2, close your parentheses, divided by 0.0219, and we get approximately 21 years. And it'll take approximately 21 years after 2013, which was our initial year. Now, in previous sections, we looked at interest that was compounded at different rates, sometimes quarterly, sometimes monthly, sometimes daily, but there's also interest that's compounded continuously. If interest is compounded continuously, our formula, again, we're using P because it's a population growth of money, is equal to your initial amount times E to the KT. Some books, when they're talking specifically about interest, you may also see it this way. P sub 0 E to the RT. K and R are both rates, the rates at which it is growing. So let's look at a specific problem here for interest compounded continuously. We have $2,000, so that's our initial amount. $2,000 is invested at an interest rate K that is compounded continuously, and when in 5 years' time, it grows to 2504.65. So this is when t is 5. In 5 years' time, that's how much we have. We want to find the interest rate. What is the rate, or what is K? Well, we can use our equation. We know that when time is 5, we have this much money, $2,504.65. That equals the initial amount, E to the 5K. We can divide both sides by 2,000. And that leaves us with E to the 5K. Hopefully you're beginning to see a pattern here. If I take the natural log of both sides, we get 2504.65 divided by 2,000 equals 5K times the natural log of E, which is 1, so we don't have to put it. Now I can divide both sides by 5. And we can get what K is. So the natural log of 2504.65 divided by 2,000 divided by 5 is our K, and we get 4.5. Well, we get 0.045. So the interest rate is 4.5%, but for K we will use 0.045, or a 4.5% interest rate. Okay, the next thing I want is the exponential growth function. So P of t is our initial amount times e to the 0.045 t. That is the exponential growth function. Say I want to find the balance after 10 years when time is 10. Well, we have P of t, and you simply input this into your calculator. And if we put that in, we have 2,000 times e to the 0.045 times 10, and you should get $3,136.62. Since we're talking money, you can have cents. If we were talking a population, you can have a part of a person, you'd either round up or round down. Okay, just like we did on the previous problem, we want to find out how long is it going to take this to double. So if we think about doubling this, again, remember if our initial population, I'm just going to use population at 0, e to the 0.045 t, and then twice the population at 0. Notice these will cancel each other out, and we have 2 equals e to the 0.045 t, and you can always use this for doubling the population. You could go straight to 2 equals e to the 0.045 t, and in a minute we'll see another shortcut. Take the natural log of both sides, and we get the natural log of 2 equals 0.045 t times the natural log of e, which is 1. So this is the natural log of 2 divided by 0.045 is equal to t. So if we're going to find how long it's going to take this population to double, we get about 15.4 years. After the initial deposit. I don't think we said when we had deposited this initially, but it's going to take about 15.4 years to double, let's just say, to double. Right? Okay, we're going to come up with a quick formula to help us. The growth rate, which is k, and the doubling time, t, are related by the equations k times t equals the natural log of 2. So we could solve for k, and that would be the natural log of 2 over t. Or we could solve for t, and that's the natural log of 2 over k. So this is a quick formula that we can use to help us with the growth rate and doubling time. Doubling time, that's what we're looking at here. Now, not all populations can grow exponentially. Some have a limited growth. For instance, they may grow up to a certain point, and then because of different factors, such as if you had fish in a pond, other fish, or different things, food source availability, there might be a limiting factor. And a model of limited growth can be represented by this equation. The population at time equals 0 is equal to a, which is the limiting factor, over 1 plus be to the negative kt. This is called a logistic function. The function increases toward a limiting value of a as the population increases. If we were to look at a graph, y equals a would be a horizontal asymptote in this case. All right, so let's look at an example. We've got limited population growth in a lake. A lake is stocked with 400 fish It's stocked with 400 fish of a new variety. Okay, so this is a variety that's not been in the lake before. The size of the lake, the availability of food, and the number of other fish will restrict the growth so that it's a limiting value of 2,500. As the population gets closer and closer to the limiting value, it'll get close, but it'll never actually reach it. So the population of these fish at any time is given by the function 2,500 over 1 plus 5.25 e to the negative 0.32t. Okay, if we wanted to find the population at various time functions, there are months throughout this, you can put this function in your y equals. That's what I would recommend that you do. Put this function in your y equals. Be sure that you put the denominator in parentheses. Now, once you get that into your y equals, you might pause this, stick it in your calculator in your y equals. Remember, I told you the other day that you can hit the VARS key, that's for variables. So if you hit the variable key, then tab over to y variables, hit number 1 for function, and whichever place you put that in, you need to, if you put it in y1, then just hit 1, open your parenthesis, and type in 0, and you should get 400. Then you can do the same thing for other values. In fact, you could even do second enter and back up and change that 0 to a 1. And if you do that, you should get 520. You could do second enter, back up and change that 1 to a 5. And if you do that, you could get 1214. And so you could easily find at any number of months what that population is. If we checked at 20 months, we see that it's approximately, and these are all approximations, 2478. So notice we are reaching that limiting factor. Let's see what happens. Let's see what happens if we checked at 30 months. So notice we get 2499. It's almost 2,500, but we'll never actually reach 2,500 because of those limiting factors, the other fish in the pond, the size of the lake, the availability of food. So this is a limited growth model. We looked at exponential growth, and with exponential growth, we said k was greater than 0. But if we look at exponential decay, the function is p sub 0 e to the negative kt. Now here I'm going to say k is greater, well, we could say k is greater than 0, but notice that it's negative. So we have exponential decay when we have a negative rate of growth. This is called, k is the decay rate. In your science classes, you've probably looked at things that have half-lives, different chemicals, different compounds have a half-life. There's radioactive decay. And the decay rate and the half-life can also be described with the same relationship that we looked at for doubling. Because k is negative, you're going to still end up, it'll give you the half-life. Let's just look at how we could get a general expression for half-life. If we took half of the original value, again, we're looking at a decay rate. So this is a negative kt. Again, these cancel out. And we would have 1/2 equals e to the negative kt. Now remember, I can rewrite 1/2 as 2 to the negative 1. And if I take the natural log of both sides, it becomes a negative natural log of 2 is equal to negative kt times the natural log of e, which is 1. So if I wanted to solve to find out what the half-life is, in other words, I'm wanting time, it's the natural log of 2 over k. So that's the same thing that we got when we talked about the doubling rate. So time is equal to the natural log of 2 over k when we're talking about half-life or decay rate, or the decay rate is equal to the natural log of 2 over time. All right, in your books on page 375, you have an example of carbon dating. And I want you to look at that example. It shows you an example of a decay rate, how you would find that, and then you will actually use that one on one of your homework exercises. You'll use the same half-life of 5,750 years, but I want you to read that problem and see how it's worked out. And your assignment, this is assignment number 7. And your assignment is on page 376, 1 through 9 odd, 11 A through D, and 15 and 17. Okay, we'll work on this. This is your assignment that's due on Thursday. On Thursday, we'll work on some more of these problems, and on next Monday, you will have a quiz over these applications of exponential growth functions, exponential decay functions.